Hi everyone, welcome to your third Honeybee generation tutorial. In this tutorial we're going to get down to business and analyze the financial value of the PV generator system which we created in the previous two tutorials. And once we've done that, we're then going to add a wind turbine to this Energy Plus simulation. So the Energy Plus simulation has finished running, and now we're going to look at the results of the energy use of this Honeybee zone here, and also the energy generated from this PV generation system here. So come up to Honeybee, come to Honeybee read generation system results, come to result file address, IDF address, and it will just take a minute to read those results in. Okay, so now we've got the results in, and let's look at the four outputs that we've got from the Energy Plus simulation. So the first output here is total electric demand. So for every hour of the year, this is the demand in kilowatt hours for the whole facility within this Energy Plus simulation. Since we've only got one Honeybee zone, the demand that you see here is just simply the demand of this Honeybee zone here. This starts at 1 AM on the 1st of January, so it's 8,760 hours and goes all the way to the end. Okay, so now this is the more interesting part. This is the net purchased electricity. So what this means is that at every hour of the year, you have your PV generator system back here generating electricity. Now, if the PV generator system generates no electricity in a specific hour, what you'll see is that the net purchased electricity is the same as the demand, say for the first hour of the year, 0.52, 0.52, and that's the case because obviously in the middle of the night, PV generator systems are not going to be generating any power. However, as you come down a few hours into the year, so I think this is the first 4 days of the year, you'll see an hour where it's actually negative 1.46. Now what that actually means is that this PV generator system has generated more electricity in that hour than the building needs. In fact, it's generated 1.46 kilowatt hours more energy than electricity than the building needs, and so it's fed it back into the grid. And you'll also see at some point these numbers diverge because the PV generator system is powering the building at various hours throughout the year depending on the sunshine. So that's what net purchased electricity means. Now this is actually the energy that's produced by this Honeybee generator system here throughout the year. And as you can see, I mean, this net purchased electricity is the difference between the total electric demand and the generator produced energy. And as you can see in the first hour, I'll just go back to the first hour here. And as you can see in the first hour, it's 0, while this is 0.52, so this one's 0.52. So that's how that works. If you've got several, don't worry about what I was saying there. Forgive me here, this does actually need to say US dollars. I'm going to fix that up right away now, but what you've got here is the financial data of this Honeybee generator system. Now we've got 4 PV generators, because if you come back here, there's 3 Honeybee surfaces coming out of this PV generator component with PV generators attached to them, whereas in this PV component there's only one Honeybee surface coming out of this component with one PV generator attached to it. So that's why you've got 4 here. So you've got 4 PV generators at $1,200 US each. The inverter cost is $2,000 US. The system maintenance cost is $400 US. So that's the financial data there. Like I said before, I will be putting US dollars there. It should say that. My apologies, I'll fix that up. Okay, so that's the raw data from the IDF, the simulation. So now what we're actually going to do is we're going to visualize and analyze that data further with this component here, the Honeybee visualize Honeybee generation cash flow. And what you need to do is you need to put all these links here into input data. And okay, so we've got our input data. Now what we need to do is, in order to actually calculate the financial value of this system, you of course need the cost for electricity from the grid as a schedule, and you also need the feed-in tariff as a schedule, because at the moment I haven't implemented the ability for Honeybee generation systems to store electricity. So at the moment it's simply assumed that all electricity that is not used directly on site, so if there's an excess of electricity for 1 hour of the year, it will simply be fed back into the grid and income will be generated based on the feed-in tariff. So just to be clear how this works again, and it's specified here in the documentation. If you have an hour of the year where there's excess electricity generated, the PV generator system will generate a revenue first by saving the facility from buying electricity, and that will be however many kilowatt hours of electricity were used in that hour by the facility multiplied by the grid electricity cost for that hour, plus the revenue from putting the excess electricity back into the grid at the feed-in tariff rate. So I hope I've made that clear enough. Like I said again, it is specified here, and in the future I will be adding the ability to do all sorts of more complicated things with energy storage and such like. So what I'm going to do here is we have a grid electricity cost schedule. Now you can just put a flat grid electricity cost. If you just put one value, that will be used for every hour of the year. If you don't put one value, you need to actually create a list of 288 values. One value for every hour of the month of the year. So what that means is that here, this is actually 1 month. We've got 23 values multiplied by 12, so we get 288. So this, for example, is the 1 a.m. in 1 month, 2 a.m. in that month again, 3 a.m. in that month again. So only 1 day is represented for each month. That's how this schedule works. Then also the feed-in tariff, let's put it up here. Okay, so now the components run, and what you actually get out before we look at the graph, or before we graph something, we've got the financial value of the generator system in net present costs over 25 years. Okay, this should really actually specify 25 years, so I will fix that up for you. So this is the net present cost in today's money of this generator system in US dollars over 25 years. We can also graph this, we can also graph it by system, which in this case won't work. I'll show you that a bit later because we've only got one system. Or we can graph it by cost, so we'll just do that, and it does take a bit of time to do this, so I'll just pause the video. Okay, so now we've drawn the graph, and you can actually see the net present cost by cost type over 25 years. Now this is assuming no discount factor. You can actually set a discount factor. We'll make it 6%. And yep. So this is the net present cost by cost type over 25 years. So you can see it year by year. So we've got maintenance costs, and then we've got replacement costs, which in this case would be the inverter, because PV panels are assumed, and it's stated in the documentation that I've written, they're assumed to last for 25 years. This is the initial outlay of the capital costs investing in the system. And this is the generation return. This is the return that this system gives every year, in both saving money because the building doesn't have to buy electricity, but also by feeding excess electricity into the grid and getting that feed-in tariff. So that's how this financial component works. Now let's look at adding a wind turbine to the mix. So if we come back here, this is all the PV generator geometry. And what we're going to do is we're going to add a wind turbine. Okay, so if we drop the wind turbine on the canvas. Now, as you'll see, there's a lot of properties with wind turbines because they are quite complicated. So what you can do is there's two templates here which are taken from Energy Plus. A template large turbine and a template medium turbine. You'll also need to specify a unique name for your turbine. So if you just want to use the template of the large turbine, then you can see the properties here in the README. Or you can use the template of the medium turbine, and you can see the properties again here in the README. Now, with these properties, you can change any one of these template properties by simply connecting, changing one of the properties here. So, for example, okay, let's choose the quickest one. Not good. So you can change any one of these properties here. Let's change this to, what is it now? It's 77. So the cost now is $77,000 US. So let's change it to 90,000. So we've changed that to 90,000, but we've kept all the other properties. They haven't changed at all. Let's change the cut-in wind speed. The rated wind speed now, it's 11 meters per second. So let's just try 15. Yep, so now we've changed 15 meters per second, but we haven't changed anything else. So you can play around with the template like that. So that's basically the wind turbine component. Let's add it to, let's create another generator system. You could add it to this generator system, but I want to show you what the financial analysis looks like with another, oops, wrong component, with another generator system. Okay, so let's connect the turbine here. Okay, so let's call this wind turbine generator system. Okay, let's set the maintenance cost to $500 a year. Okay, let's connect that again up to Energy Plus, and we'll let it run. Okay, now that simulation has finished, we can see the effects of adding a second Honeybee generator. So first in the read Honeybee generation system results, we're actually seeing the generator produced energy. Now we have a data tree instead of just before a list, and the reason being is that with two generators you're actually producing two different lists. So the okay, so this is the electric energy produced by a generator system named PV on. So that's by the PV system, and then this is the electricity produced by the wind turbine, and you can see there's many hours there when nothing's produced, and then there's some hours there where quite actually a bit is produced. So that's that. Now on the financial side of things, we now see also that we've got a data tree on the value of the generator system. So the wind turbine actually produces a negative value. So that means that it's not actually worth investing in this turbine. And over 25 years, you won't actually get your money back because the net present cost is negative. So let's have a look at the graph that's being produced with two systems. And with this component, if you've got multiple generation systems and you set to true graph data by cost, this is actually the combination of those two generator systems. And you'll see in comparison to the previous result where we only had the PV generators and not the wind turbine, now we've got a huge capital cost, which is the wind turbine, and then much smaller revenues over 25 years. So that's why we're getting this negative value here. In addition to that, you can also have a look at another graph, which is graph data by Honeybee system, and it may just take a few minutes, so I'll just pause it. Okay, and now we can see the net present cost by Honeybee system over 25 years. So as we can see, this is not the cost by type, but the cost for the whole generator system. So the wind turbine, we've got huge capital costs, and then we recoup just a little bit over 25 years. And we've also got some maintenance costs in there, where the PV generators, we've got very small capital costs in comparison to the wind turbines, but we get a much better return on investment over 25 years. So that's why we've got this negative net present cost here for the wind turbine. So it's basically not worth it. Last but not least, if you want to use Galapagos to optimize your generator system, of course you're actually going to need these numbers. So how you would do that, if you've got several systems, first you would come and use this tree branch component, connect the tree, set the path to 1 for the first, so that will be the PV on HB zone, and then for the second one set the path to 2. Oops, what happened there? Oh. Okay, not sure why, maybe I need to, okay, there we go, sorry about that. So set the first one path to 0 and then the second one path to 1. Okay, so once you've done that, then come to the Ladybug. Sometimes I have used this component before. There it is. So no, not that one. Ladybug separate data component. So come up here to the Ladybug separate data component. And what you need to do is just put that data in. And you'll see on the output, you've got numbers. So that's what you can use for your optimization. Okay, well that concludes this series of tutorials. I hope that you find these components useful, and I will be adding much more functionality in the coming months. If you do have any user requests or technical issues, or you find any bugs, please do contact me. My email is within all of these components here. That's my email there. So if you open up any of these components, you'll see my email. So thank you for watching, and enjoy.